when we're looking at applications of the effects that we talked about, so we've talked already about sort of the motor effect and your electromagnetic induction. And we're now basically trying to show you how we apply these concepts to basically create motors. So different types of motors, but we apply them to sort of get to motors. And what exactly is a motor? Well, a motor or a generator, different things, but a motor basically is something where you take electrical energy, you put it in, and it starts turning, you get kinetic. And we can also apply them to generators. So generators is the opposite. You start with things that are turning. And you get them electrical. And your motor, if you like, is something that is going this way. You take electrical energy, and make it into kinetic. And the question, I suppose, is how do we do that? Well, we're basically going to use the motor effect. So what do we mean by the motor effect? Well, it's basically one of the things we said yesterday, which basically refers to the fact that, you know, if you have moving charge, or we can simplify that to current in a magnetic field, then it will experience a force. It's a sort of very short version. So typically for motors, we're referring to F equals BIL sine theta, because typically we're measuring currents here. But if that is the case, then basically, if you've got a moving charge in a magnetic field, you experience a force. So think about this, right? If you end up getting a force, that will then provide acceleration, and therefore things will start moving. So basically, we're going to supply current, and then, you know, due to the fact that we supply current, then due to the motor effect, we're going to get force, which provides acceleration, which then gets it moving. Okay, that is the very basic idea behind it. Now, you've got different types of motors, and let's start with a DC motor. But basically, a DC motor relies on the fact that you need the motor effect, and you know that the motor effect means you need a current and you need a magnetic field. So basically, you need a magnetic field of some description, and we're going to start with using permanent magnets, but obviously this can change. And then, well, you'll need something to carry the current. So that's your wires, which we typically call up. And with that, you know, you've got your magnetic field, you've got your coil. The coil is what carries the current. The magnetic field is your, you know, the two provided interact to produce the force. Okay. Once the two interact to produce the force, then that gives you it will start to turn, all right? Assuming you've got a torque. So DC motor, typically, example, you'll have north pole here, south pole here. That means your magnetic field is like so. And in a 2D diagram, you know, we might have your coil kind of going like this. And so the current on this side, let's say it's going in and it's coming out. And if you use your right-hand palm rule, then you can see that if it's going in, it will experience a force downward. On the right-hand side, because the current is going outward, then you experience a force upward. And because torque, which is what you need to get things turning, is equal to force times distance, and you can see that this center is here. So you've got this distance over here. So that will create a torque. Now the torque, because the torque is going to equal force, and I'm not going to derive the formula. I think that, you know, in the interest of saving time, this force is going to equal BIL sine theta. But just note that no matter where this, you know, think about what we said yesterday. These are going in and out, so you can kind of have your pen pointing in or out of this, you know, of the page, and it's going to the right. So this, therefore, is going to equal 90 degrees because, you know, going left or right is perpendicular to in and out. All right. And so that's going to be your BIL sine theta. For the force, your distance is going to be, well, half the radius. Putting all that in and doing a little bit of things, then you'll basically get your torque equals BIA. Well, it will become, if you guys are going to use, you know, your formula sheet uses sine, so I use sine. So basically, you might have an N here. This is the number of coils. So basically, for each coil, you'll produce a torque, and I'm only looking at one coil here. But if I double it, triple it, obviously the effect will double or triple as well. So N is the number of coils, E is the magnetic field, I is the current, A is the area of the coil. So remember, this coil is actually, you know, like that. So we need to work out the area. Which, you know, you can just think of as length times width, where this is sort of W. Now, alpha is not theta, all right? You know, your formula sheet will have it as theta, but I'm writing it as alpha because, you know, lots of people think these are the same thing. They're not. So, you know, theta just represents an angle, but you need to understand what that angle actually is. So alpha, if you're using sine, if you're using this formula, which is what's on your reference sheet, then is the angle between the normal and the plane of the coil. So, you know, in my example here, if the coil is going to start to turn. If it starts turning, then you'll get something like this. And the force, we'll note, does not change direction, nor does it change magnitude because it's still 90 degrees, because, you know, they're still perpendicular. But the torque will actually change because this plane, well, so this is the normal. Right, so this is the normal. And so this angle here would be alpha. The angle between the plane and the normal, oops, wrong one. The plane is black, the normal is there. That would be it's the angle. So if it was that, it's the angle between the plane and the magnetic field, or if it's between the normal, it's between, okay, it's between the normal and the magnetic field. I was right the first time. Yep. So I should rephrase that. It's between the normal of the plane and the magnetic field. So what you should notice is that the magnitude of the force does not change, you know, as it turns, so to speak, but torque does change. And you get tested on this quite a lot. So basically, in this situation, you'll get max torque. This is a max torque situation, all right? And by the time you reach vertical, it will be no torque. So it'll keep turning, but once it keeps turning, it will reach a position where it's like this. The force will still be going up and down. And you can probably understand just from a general idea that, you know, that doesn't give you any torque. So my normal is going to be like this, which is going to be perpendicular to the plane. And so when we take the sine of the angle, so it's going to be parallel to the magnetic field. And you can see that if we use this formula, that means the torque in that situation will be 0. So this is minimum torque, or torque equals 0. Okay. And so the torque of a DC motor will vary as it turns around. So remember your DC motor. Key parts you require, just in terms of concepts, to get it moving. You need a magnetic field and you need a wire. Now, physically, we split this up into what's called a stator and a rotor. So a stator doesn't move, a rotor rotates. So in my example there, the stator is the magnet, the rotor is the wire. Okay. So once you have that, then note that force doesn't change, at least at the level we're thinking about it. The torque does change based on the angle. And that's why typically you'll get questions about, okay, as the motor turns, you know, what is the sort of graph of, say, force and torque? And so, you know, your force, if you're graphing force against time, because you understand F equals BIL sine theta, but theta equals 90 degrees, then it's going to be BIL. Now, the magnitude doesn't change, but the direction does, because, you know, I've only drawn it turning like 90 degrees, but when it goes over, what you actually, you know, assuming you want to keep it turning, you now need the force to no longer be up on that side, but down. And that's why you have what's called a split ring commutator to change the current direction. But that means the direction is going to change. So that means you'll get something that looks kind of like this. And if you'll do a graphing torque, this is time, because of the changing direction, you're helping it keep spinning. It's going to look more like your sine graph, but the absolute value of a sine graph. Okay. So that's basically what the torque aspect is about. Now, as far as your, you know, there is a back EMF aspect. So back EMF relates to our electromagnetic induction. So basically it refers to the fact that as the coil spins, and just, you know, think about it from this point of view, as it spins, it will experience a change in flux. And, you know, maybe just think of our diagram here and maybe just look at this. The coil is like this, it's flat. And so there's no flux lines passing through. So this is a case where theta equals, not theta, phi equals 0, flux equals 0. And when you turn, you know, the flux is, well, some number, because you've got some lines are passing through now. But, you know, this one, more, I mean, I only drew 3, but the point is you can see that, well, that line didn't pass through, whereas that line does pass through now. So this is, the flux going from here to here has gone up. And as it turns the other way, it's going to start going down. And so the short version is that as it turns, you'll experience a changing flux. And because it experiences a changing flux, that will induce an EMF by Faraday's law. And that EMF must oppose the supply voltage. And that would be due to Lenz's law. And that's why it's called back EMF, because you're going against the supply voltage. So basically, as the motor spins faster, then it takes less time to spin around once, so that the time taken will go down. So delta phi over delta t goes up. So, you know, the EMF induced goes up. So basically your back EMF essentially will rise until it, you know, it hits an asymptote for the operating speed of the motor. Your supply voltage will simplify as just, you know, constant. And so your voltage across the coil is basically just, you know, the difference between these two, because it's your supply voltage minus your back EMF. So basically you've got your supply voltage on the left, which we're assuming is constant. And then you've got your voltage across the coil, which must equal supply voltage minus, you know, back EMF. And that's why as it spins faster, it basically starts at the supply voltage, and then it will get, you know, closer and closer to zero. Well, so it depends now if you're talking about real life or if you're talking about sort of ideal. So, you know, for an ideal motor, you know, with no friction, no air resistance, and so on, which obviously is not real life, then yeah, you know, and then no load, right? Then it will go towards zero. Well, that's not V supply, that's V coil. Well, yeah, so the graph is V coil, but the value there is, you know, starts at initial value of V supply, because back EMF is zero to start with. Now, in reality, you know, it won't reach zero because of the fact that we need to put in work to overcome friction and air resistance. And most certainly once you, you know, once you start putting a load on, then obviously the motor has to do work. But that's the general idea. So what that actually means then is your voltage is high at the start or whenever your motor slows down. And that's why, you know, the concept of back EMF, you know, you're often tested on, like, you know, why does, you know, when your motor slows down, why does it break? Well, because your voltage is higher, so your current's higher, which means there's more heat, which means you're, you know, why is it more likely to break? You know, or does, you know, why does it get hotter? Or the other way they could ask the question, I mean, it's all the same question, but why is it if you have a motor, why do you need a starting resistor? And the reason is because, well, if you don't have a starting resistor, you're going to, you know, have a very high current from a very high voltage. Now, if you think about it, the motor's not going to be at this sort of stage for very long, right? Once it starts up, mostly, you know, motor, it depends on how big your motor is, but let's say it takes a few seconds to spin up, right? But then it could be turned on for hours. So this section is not really there for much time, right? Relatively speaking. So it's designed to, you know, take this amount of voltage and current because that's where it's going to be most of the time. under its operating sort of conditions. And so, you know, you can't design the motor to carry this amount of voltage and current because you need to, you know, make the motor heavier and less efficient and all that kind of thing. So if you design it for this sort of situation, then at the start, it can't really take that and it might burn out the motor. And that's why you need a starting resistor. All right. So that's basically, you know, the back EMF type of things. You need to understand that your motors are split into DC, which will require you to use a split ring or split ring commutator. AC would use a, you know, slip ring commutator. So those are the sort of names you should be using, but you can think of this as a half ring and this is a full ring. Okay. Now, there is also, of course, the induction motors. Which I know some of you have mentioned previously that you wanted to talk about a bit more. Now, the induction motor is going to be regarding the fact that, unlike the things we've talked about just now, an induction motor must firstly operate on AC. And the reason why it's called induction, kind of tying in with what we said yesterday, is because the rotor, which has wires, is not connected to the coil, to the supply or the battery. So basically, in the middle, you've just got some coils. I mean, conceptually, right? In the middle, you've got some coil. It's actually called a squirrel cage rotor. But the point is, it's not connected to any sort of power supply. So you've got your rotor in the middle, and literally there's wires there, but it's not connected to anything. And what we basically do is we create a rotating magnetic field. And so the magnetic field is basically made to rotate. So I can't rotate lines here, but basically if at t equals 0, it's like this. Then at t equals 1, it's like this. And at t equals 2, it's like this. And so what we're basically saying is, as a result of this, because we are putting the rotor in a rotating magnetic field, then because the magnetic field is changing, then the rotor is going to experience a change in flux. And because it experiences a change in flux, then it will have an induced EMF, which will then give it an induced current. And therefore, you will now have current flowing in the rotor. And because the current is flowing in the rotor, then it will experience a motor effect because it's still in a magnetic field. And so, you know, you'll have current in magnetic field. So from the motor effect, it will experience a force and start to turn. And so how is the induction motor different to the motors that use these? Well, these, you literally, you know, your rotor is a wire that is connected to the power. You literally directly pump current through those wires. Whereas if for an induction motor, this rotor has wires, but it's not connected to anything. And how you get it to turn is you create a changing magnetic field, which in simple terms is, you know, using AC. We won't get too much into detail into that, but, you know, you have places around it and you basically pass them at different times. And the end result is the magnetic field is rotating, right? So basically, conceptually, think about it as you've got a north pole here, you've got a south pole here, and you're kind of, you know, conceptually anyway, obviously it's not actually done this way. Just imagine your rotor is in the middle, and what we're doing is we're moving the magnets around. That's conceptually what we're doing. All right, we've got a north, you know, maybe so north to south, right? That's your magnetic field. Conceptually, what we're doing is we're moving the north pole, you know, clockwise, as well as the south pole clockwise. So the magnetic field will rotate. Okay, and as you can probably guess, you know, the details are because it, you know, induced a magnetic field and all that kind of thing. But the result of this is that the rotor will also rotate. So this results in the rotation of the rotor in the same direction. And you would explain that using essentially Lenz's law, in the sense that basically you don't, the coil doesn't want to experience a changing magnetic field. And probably the easiest way for you to think about this, you know, there's applications of Lenz's laws in many ways. But one of the applications is, you know, determining which way the current is produced. But another sort of application is to think about forces. And while we could, you know, go into detail, and you have done enough work to, you know, think about this in terms of forces and so on, what you could also do is say, okay, I've got a magnet and I want to pull it away. So my change is I want to pull the magnet away. And more technically, it's the north pole I'm pulling away from the coil. That's what I'm trying to do. Now, the question, of course, is if I'm pulling the north pole away from the coil, you know, we could talk about what the flux change is and how that induces a current here and how that creates a magnetic pole and how that, you know, either attracts or repels that. But if we ignore those details, well, just think about it. Like, think about it like, you know, Lenz's law, think of it like electrical principle, like, you know, or friction, right? You want to pull it away. So this wheel not wanted to go away. So Lenz's law, oppose. So it will simply try to attract the north pole back, which means, you know, it will create a south pole. And, you know, you can use your right hand grip rule to figure out how it will do that, and that will induce a current in this direction. But the point is, it will try to, you know, stop it going away. And a bit of practice can probably help you figure that out. But applied to your induction motor, which I think a lot more people have a lot more trouble with, the way to think about it, I think, is just, you know, you understand that your magnetic field is rotating. This magnetic field is rotating. Now, I can talk to again about how the magnetic field has changed, what's the change in flux, what's the, you know, induced current and all that kind of thing. But basically, if you're something and you don't want a change, then, you know, you basically don't want any relative movement, right? So if the magnetic field is moving, you don't want the magnetic field to move relative to you, because otherwise that's a change in flux, right? And, you know, Lenz's law says you don't want to change. And so basically, if the magnetic field is moving clockwise, then you'd also spin clockwise. And that's probably just an easier way to think about it. So, I mean, it's skipping over the details, but basically, as the magnetic field rotates, the induction in the rotor in the induction motor will also rotate in the same direction. And that's basically how you're going to get that to work. That's how basically induction motors work. Now, before I continue on to electromagnetic braking, just going back to some questions that you guys had. So the voltage of the coil is the voltage across the coil. So, you know, if you've got a coil and, you know, you've got your commutators and brushes, which I won't draw in, but, you know, you've got a battery, right? And you've got a battery that, you know, supplies voltage and current. Well, that would just be the voltage of your supply. You know, as we spin up, as this spins up, your back EMF is going to increase. So the voltage across the coil, so, you know, literally if you, you know, had a voltage measuring here and here, it's going to drop because of the back EMF. In other words, you can think of the back EMF as, I mean, conceptually, if you like, I mean, obviously it doesn't actually, you don't actually have this here, but the back EMF, if you like, is kind of like a battery that gets stronger the faster it spins. So it's, you know, these two batteries are going to fight each other, right? Is what I'm basically saying. So V coil is the voltage across the coil, and I'm saying that it will drop as it starts to spin faster, because conceptually it's like having this battery and it's going to get stronger. So it's a variable voltage. And so these, you know, this battery wants to push current clockwise. This battery wants to push current anti-clockwise. And, you know, if you spin fast enough in a situation where there's no friction, then these voltages will equal. So the voltage across the coil will be 0. Now, I had also mentioned that the torque, the force will stay constant, but, you know, vary. The torque due to the angle between the changing will just be a sine curve like this. Now, ideally, we don't want a torque that changes. Ideally, we want a torque that is flat. Now that's, you know, a bit hard to achieve, all right? But what we basically have so what ideally you want is a flat torque. That's what, you know, ideally you want flat. This is ideal. Now, obviously, you know, you don't have that, right? I mean, you know, before you turn the you know, current around, you actually had a sine curve. Like originally you had a sine curve. And that's not very helpful, because it just means, well, your coil is going to turn 180 degrees and then back 180 degrees, and it's going to repeat that. And so the first thing we did is we used, you know, your, where did I write it? We use your split ring commutator to change the current direction. And because the current direction changes, then so does the torque. And so your first thing is to, you know, flip that over and make it the absolute value. But obviously that's still not great. You're going to have instances on time where you have no torque. And so there are improvements you can make to this motor. So one thing you can do is you could have more than one coil, right? And you can have more than one coil at, you know, you can have more than one coil at, you know, 90 degrees to each other. So basically when one coil is at minimum torque, imagine if the blue line was the second coil, then the blue coil would be at maximum, because, you know, it's in this situation here for the black, right? So one will be at maximum and one will be at minimum. So one way you could kind of improve this is, okay, so you had the green one, and then, you know, which is now going to become like the green red, and then I could have a white, a yellow one, which looks like this. And that's a situation where, you know, the maximum for this one is the minimum of that one, and that repeats forever. So that's kind of like having them two at 90 degrees angles. And then what we could do is then we could just always take, you know, we could use switches and so forth to always take the one that's higher. And so you can see how this is getting closer, but obviously still not, you know, it's not flat, but it's a significant improvement. And, you know, we could have more coils. So, you know, 3, 4, 5, and so on. So that's one way to do it. So in terms of improvements to the torque, we could have, you know, coils at different orientations. So they sort of make up for each other, and you just connect it up appropriately. Now, the other improvement we could make is we could use a radial magnetic field. Now, that kind of needs you to understand what a radial magnetic field is. And let me perhaps draw it here on the bottom left. And a radial magnetic field is basically, as the name might suggest, like radial, so radius. So it's like a circle, right? That's so basically, you know, instead of having this and this, which is what we had originally, you know, I'm exaggerating, and I'm also not going to draw it the proper way because I'm going to demonstrate the point rather than draw it, you know, properly. So if this is the North Pole and this is the South Pole, then, you know, essentially, instead of having the, you know, the lines going left to right, basically they're going to, in this case, I'm not sure what's going on there. Okay, should hopefully work. We're saying that they kind of do this. So a radial magnetic field results in this situation where, I mean, I'm not drawing it properly, but you know, the radial magnetic field actually doesn't look this way, but the concept is correct. So basically, the magnetic field lines are not horizontal anymore, right? They're not horizontal like this, but rather, I mean, properly you would draw it kind of like this thing, but conceptually, your rotor at, I can't say all angles, but at a larger number of angles, you know, stays closer to 90. So if we calculate torque using, you know, sine alpha, basically the effect is that its alpha is 90 for longer. And in the extreme ideal case, it's at 90 degrees all the time. So in other words, we reduce the variability. And again, we get, so take the extreme case where alpha is 90 the entire time, then this is just one and you just get NBIA. And so, you know, you'll get your, you know, ideal torque. But obviously that doesn't actually, you know, happen. As for when the force changes, hopefully that's quite obvious. You know, as we were drawing here, depends what angle you're talking about, but if you think of this as 0 degrees, so not alpha, right? But if you think of this as 0 degrees, then, you know, as it turns, the force is still up and up. So when it gets to 90, you know, you remember you're trying to get it to turn like anti-clockwise in my example, right? So it's turning anti-clockwise, it's going, you know, that way. So, you know, you're trying to go anti-clockwise, but once it goes over, if the force is still up and the, you know, and this is still down, then it's now going to start, you know, trying to turn clockwise, which is not what we want. So basically every time in my example here that it's vertical, so you can think of that as 90 degrees if you like, or negative 90, or whatever you want to think of it, anytime it hits this situation, it's going to, you know, change the force, right? So that hopefully should address all the questions that have been sent. And now let's quickly look at electromagnetic braking. So electromagnetic braking is as you might imagine, it's basically, use of brakes using, well, electricity. But I guess it's really electromagnetism. And so the way we do that is quite simple, actually. So we're not talking about regenerative braking, although that's quite similar, but that's not what's tested in your HSC. But it is similar in concept, but different in implementation. So imagine, for example, our wheel is rotating, forward, right? And we've got this sort of area where we can apply a magnetic field. So we can, perhaps we've got a magnet that we can bring close or further away. So that's probably like a simpler design in, if you buy some gym equipment and they could use, normal brakes, just friction. They could use what's called friction brakes, but you could also get what are called electromagnetic brakes, where they might do a simple design where they just bring a magnet closer and further away to turn the magnetic field on or off. But if you're doing it in a car or a train, you're probably using electromagnet to do it, all right? But anyway, the point is there's this area here where we can turn on or off the magnetic field. And, if there's no magnetic field, then the wheel kind of just turns as it does, and, well, that's that. Now, what we can do is we can go, hey, we want to stop. And what we will do is, you press the brakes, and if you're using electromagnetic braking, what that would do is it will turn on a magnetic field on a part of the wheel. So it doesn't really matter which way the magnetic field goes, but I'm going to do it as into the page here. Now, imagine you are point A of the wheel. You're going to rotate, and you're going to go to A prime, right? The wheel's rotating, you're a part on the wheel, you were here, you're going to go there. And so if you consider, A to A prime, like the point that goes from A to prime, you'll hopefully notice that here it's in the magnetic field, here it's not. So it experiences a change in flux. And because it experiences change in flux, then, dot, 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 by Lenz's law, it's going to induce a current. This current will change, oppose the change in flux. So it used to have into the page, it doesn't anymore. So it wants to create an into the page. So, induce current and so on. So what it wants to do is induce a current that will create an into the page direction. And using a right-hand grip rule, you'll find that if a current flows in that direction, it will create an into the page here, and that will try to minimize the change. And you could also consider B and B to B prime. It doesn't matter too much, but if we were to consider the point B, which will then rotate to B prime, then what happens is it wasn't in the magnetic field, now it is. So it's gone from no flux to there is a flux. So it will try to counteract that into the page change. So it will create one out of the page. And you'll hopefully, with your right-hand grip rule, be able to see that that will create on this side something like this. Now, importantly, these are induced currents. But because they're currents, I mean, they might be induced, but they are currents. And because you've got a current, well, that means we now have a current flowing in the magnetic field. And because you now have current flowing in the magnetic field, then, by the motor effect, it experiences a force. And you can think of the right-hand palm rule, your magnetic field is going in, your current's going up. This force will be to the left. So therefore, this will then generate a force which I will probably have to use a different color. Let's do that. And then let's draw that. So that will generate, therefore, a force left. So that is going to give you the force. And we'll note, so that's given in maroon. And therefore, you can see that this force opposes the rotation of the wheel. It will create a counter torque. So in other words, it will slow the wheel down. And that's where you've got, that concept here. Wheel rotates, causes change in flux. Due to change in flux, creates induced current. Due to induced current, motor effect. Motor effect is, in this case, pushing left, so it will oppose that. And you can try, rotating it other ways, and, you can try doing the magnetic field the other way. It doesn't matter. The fact of the matter is, due to Lenz's law and motor effect, therefore, you'll end up, reducing the speed at which you turn. And that's that. So I'll just pause there. And are there any questions with that?